Hey kids, Smath here, and I got a short video for you today on writing Lewis structures, both ionic Lewis structures and covalent Lewis structures. So they're quite a bit different, and we need to identify how are we going to know if we have an ionic Lewis structure versus a covalent Lewis structure. So the best way to find out is to look at your bond types. If you only have covalent bonds, you're going to have a covalent structure. If you have any ionic bonds, then you have an ionic Lewis structure. And so I have three examples for you here of ionic Lewis structures. Very straightforward. I have lithium fluoride here first, and I take the lithium and the F, and underneath I've written their electronegativity values. Those I just pulled off of the table that are in the Bluebees that are sitting there on your desks. So pulled out the values. Fluorine is 4.0, lithium is 1.0, and the difference between those values, absolute value is 3.0. That means I have an ionic bond. So then what I do is I come over next to it and I write lithium. I make that one dot. Then I write fluorine. Fluorine has 7 dots. Put them where we showed you to when we did Lewis dot structures. Fluorine has 7. The element with the higher electronegativity is going to gain electrons until it has a full octet. So that lithium electron is going to get transferred to the fluorine. Now, at that point, we've just created a lithium cation, and now we've created a fluoride anion. And what I've just done here is drawn the Lewis structure for an ionic compound. I have to use brackets to signify that it's an ion. I put the charge in the upper right-hand corner, and the cation rarely has any electrons. Usually doesn't have any. And the anion has 8. So that's what a Lewis structure for that ionic would look like. What happens if there's more than one? Now, in this case, we got calcium chloride. So again, don't ever change an electronegativity value. Calcium is 1.0, chlorine is 3.0. I subtracted, it's 2.0. I know there are 2 chlorines, but we're not interested in that. It's individually calcium to 1 chlorine. So in this case, I draw my calcium. Calcium has 2 electrons. Matter of fact, for this model, I'm going to represent those with X's. There's no law that says I can't use an X or a dot or any sort of special symbol to signify those electrons. Then I'm going to put a chlorine and another chlorine. Now, each one of those chlorines has 7 electrons. At this point, most of you can see if I put one of those electrons with that chlorine and one of those electrons with that chlorine, the chlorines will have a stable octet. And so that's what I'm going to do. I'm going to just take that electron and that electron away, and I'm going to place them over here, over here. Now, when I transfer those electrons, I am responsible for making a bracket and saying, by the way, that calcium just became 2+. Why'd that become +2? I don't get it. Well, we moved 2 electrons. So if you move 2 electrons, you went +1 when you took the first one away, and you went +2 when you took the second one away. Those chlorines each became -1. At this point, we've given it due diligence. We don't have to rearrange the chlorines and put them anywhere. What's going to hold this molecule, this ionic compound together, is the electrostatic attraction between the positive chlorine, calcium, and the negative chlorines. So it doesn't really matter. They're going to rearrange themselves the way they should be present in an ionic crystal. Okay, so that's how we do one if there's more than one ion present. Keep in mind now, all polyatomics are going to contain a polar bond, but in compounds, polyatomics are going to bond ionically. So what do I mean by that? Well, as soon as I see a compound here that looks like sodium iodate. So IO3 is an iodate, and I know that because it's just like a chlorate, except it's iodine. We had chlorate, we had bromate, we had iodate. That was on our polyatomic ion sheet. At that point, since I know that that's a polyatomic ion, I now know that I have ionic bonds and I have polar bonds. I have two types of bonds. I have an ionic bond and I have a polar bond. What do we do with that for drawing a Lewis structure is very simple. This is the easiest of easy for you guys. Take your sodium, throw it in a bracket. Matter of fact, make it red so we know that it's an answer. Take your sodium, throw it in a bracket. Look on your periodic table cheat sheet and go, sodium's in the first column, so it's going to form a +1 ion. Then we all remember our polyatomic ions, and IO3, throw it in the bracket and just make it minus. Now here's the takeaway. You don't have to do anything special with the IO3, just throw it in a bracket, make it negative, and these polyatomic ionic compounds are going to have ionic bonds and polar bonds. They have both types. You have to write both types of bonds to get full credit. So if I say, what kind of bonds are present in sodium iodate? You must say ionic bond and polar bond. When you draw it, you have to use the square brackets. Don't get too fancy on me. And you have to designate the charge in the upper right-hand corner. So there are 3 examples of ionic Lewis structures. Okay, now let's look at a couple of covalent Lewis structures. In a covalent Lewis structure, excuse me, the central atom is usually written first in a molecular formula, but it may not be written first, but it's always the one that makes the most bonds. How do we know how many bonds something can make? Well, it's just like its Lewis structure. Okay, it goes up to 4 and then it comes back down. So it crescendos up. Notice we're not counting the d orbitals here. D orbital bonding is pretty much beyond the scope of this class. So keep in mind, the higher the electronegative element will probably get an octet, and carbon always gets an octet, no matter what. That's like a commandment of chemistry. Carbon must get an octet. So we're going to use bonds and lone pairs of the central atom. Now, this little table is a dandy little jobby to have. It's called the bonding Magna Carta. And this is a Smathism. No one else does this kind of stuff. But what I've put together is the valence electrons, the charge, the bonds, the lone pairs. So when I say use bonds and lone pairs, there's the bonds and there's the lone pairs. Okay, the rest of it will be making sense more of as we delve deeper into this bonding unit. So we have a molecular formula of H2O. The first thing we need to do is figure out what kind of compound do we have? Is it ionic or is it covalent? So I take my electronegativity values. I find out the difference is 1.4. So this is a polar bond, polar covalent. Therefore, I have to write a covalent structure. Now, in this case, oxygen is in group 16. Oxygen can make 2 bonds and 2 lone pairs. Hydrogen only has 1 electron. It can make 1 bond. So it makes sense we want to put the oxygen in the middle. And for those of you that watched my last video, you saw oxygen goes in the middle, give it 6 valence electrons, put the hydrogens on the outside, give them 1 valence electron, connect the dots so that oxygen will form an octet. How does it do that? Well, if we look at this molecule, oxygen gets to count both of those electrons because they're sharing. So that's 2, 4, 6. They're sharing those electrons, and 8. So oxygen has an octet around it. Hydrogen, ironically, has the next best thing to an octet. Its S is filled. So it has a duet. Sounds adorable, right? But it works. So there's my Lewis structure for water. We'll talk about later why it bends and it should be that structure. But that's how I would draw that. Let's take a look at Ni3. 3.0, 2.8. So this has a 0.2 difference. We have a nonpolar, but a still covalent bond. If that's the case, then which one can form more bonds? Nitrogen can form 3 bonds. Iodine usually only forms 1. So I'm going to put nitrogen in the middle of this. And nitrogen has 5 valence electrons. And then surround it by my iodines. And if I give iodine 7, that iodine is going to need to share 1 electron with nitrogen, and then it will have a stable octet. So if the iodine shares and shares and shares, the more electronegative gets an octet, right? Now, in this case, nitrogen was the more electronegative. So let's count how many electrons nitrogen has around it. It gets to count both of those. There's 2, both of those, 4, 6, and a lone pair, 8. Iodine very closely has the highest electronegativity, very close. It has 2, 4, 6, 8. In this model, nitrogen triiodide makes an octet for everybody. Everybody gets an octet. That makes for a relatively stable molecule, relatively stable in this case. So that's how we go about drawing covalent Lewis structures. And the only way to do this and the only way to get better at it is to keep practicing and practicing and practicing. And we're going to have a lot of worksheets and a lot of time to work on this. And hopefully we all get a little bit better before the quiz, the test, and whenever the next polyatomic ion quiz is going to be. So that's my lesson on drawing Lewis structures, both ionic and covalent. My name is Smath, and I hope this video helped you.